In this video, we're going to discuss patterns on the periodic table and the types of ions that are made from those patterns on the periodic table. So the first thing that I would like to discuss is this idea of an atom turning into an ion. Each one of these atoms on the periodic table, with the exception of the noble gases in column 8A. So every single one of these atoms on the periodic table, with the exception of the elements in column 8A, want to change their outer energy level to be more stable. Right now, we're going to say they want to change their outer energy level in order to have a full outer energy level. We know the outer energy level levels are full when energy level number 1 has 2 electrons and energy level 1 has 2 electrons, and energy levels 2 through 7 have 8 electrons. So the outer energy levels are full when this takes place. So if we look here, what we know about every single element in column 1A. What we know about every single element in column 1A, going from the column and the row, is that if you are in column 1A, then every one of these, so lithium has 2 energy levels. So we have the nucleus, and now it has 2 energy levels. Because it's in column 1A, on the outside, it has 1 electron. If we looked at sodium, sodium is in column 1A also, but row 3. Because sodium is in row 3, we have 1, 2, 3 energy levels. But on the outside, because it's in column 1A, it also has 1 valence electron, or 1 bonding electron, or 1 outer electron. We have 3 names to describe the same thing. Now, if we go down all of these, let's skip and go down to rubidium, number 5, or row 5. Now we've got 1 energy level, 2 energy level, 3 energy level, 4 energy level, and 5 energy levels. So now it's got 1 valence electron in that 5th energy level. We call this column also a group or family because they have something in common. They all have 1 valence electron. Because they have 1 valence electron, there's 2 options. They could either gain 7 more electrons. Why 7? Because the magic number, as you know, equals 8, with the exception of energy level number 2, which equals, energy level number 1, which equals 2 electrons. So in energy level number 2, it's trying to get 8. That means it would need to gain 7 more. In energy level number 3, it's trying to get 8. That means it would need to gain 7. Energy level 5, gain 7. Gaining 7 electrons is way too many electrons to gain. So instead, what all of these elements do is they decide to lose this one electron. Lose this one electron. Don't worry about where it loses it right now, but it wants to lose it. Why does it want to lose it? Well, if we were to draw all the electrons for lithium, we would see that in the inside energy level number 1, it already has 2. So when it loses this 1, it now has 2 on energy level number 1. And we know energy level number 1's magic number is 2, so it's full. If we were to draw all of sodium, we would see on this 1, 2, 3, 4, 5, 6, 7, 8 already has 8 electrons in energy level number 2. So if we were to lose this one electron, it drops back to its previous energy level, which has 8, and it's full. Rubidium, same thing. If we were to draw it back, it's got 8. So all of these lose one electron. They're all in the same 1A column or 1A family, and they lose one electron. Well, now it doesn't matter however many protons you had and however many electrons you had originally in the neutral atom. If it loses one electron, this gets reduced by 1. So then if you asked yourself who's winning if these two numbers were the same, and now the electrons get reduced by 1, the protons are winning, and they're winning by 1, so this becomes a 1 plus ion. So everybody in column 1A, when they have an opportunity to change from an atom to an ion, they're going to change from a neutral atom they change from an atom to an ion, they change from a neutral atom to a 1 plus ion. All of them do. That's why we say that they're in the same column, same group, same family. They have similar characteristics. Now, let's take a look at column 2A. If we were in column 2A, we've got a similar situation where we've got beryllium with a nucleus, 2 energy levels, but on the outside it's got 2 electrons. Then you've got magnesium right below it. The reason magnesium is also in column 2A is because it has also 2 valence electrons in energy level 3. Then if we jump down to SR, all the way down at the bottom in row 5, SR, it's going to also, not also, but it has 5 energy levels, but also it has 2 electrons on the outside. This is why all of these atoms are placed in column 2A. Column 2A, group 2A, family 2A. Well, how do we fill up energy level 2 through 7? We fill it up by having 8 valence electrons. So what do we need to do to BE, Mg, and Sr? Some may say, oh, they've got to gain 6 electrons. Got to gain 6, got to gain 6. Gaining 6 electrons is too much. So instead of gaining 6 electrons, this beryllium loses 2 electrons, and now in energy level number 1, it has its 2 electrons on the outside. So it loses this electron, this electron. What about magnesium? It's got 8 in that second energy level. So when it loses these 2 electrons, it also now has 8 on the outside. Same thing here. It loses these 2. That's why they're all in the same column, group, or family. So now we have all these neutral atoms with a certain number of protons and a certain number of electrons. But this time, the electrons were reduced by 2. So if we started with a neutral atom, reduced the number of electrons by 2, now all of these become a 2+ ion. When you lose those 2 electrons, you become a 2 positive ion. So now everybody in column 2A, there is a pattern. You start with an atom, a neutral atom. They are not happy with the outside of their atom. They're trying to reach the magic number for the outside of their atom. And what do? They change from a neutral atom to losing 2 electrons to become a 2 positive ion. So now, here, when you see periodic tables written and people write in on the top a 1+ here and a 2+ here, and some of them may even highlight it, we don't need to memorize 1+, 2+. We have an understanding based off the structure of the atom of why those atoms change, because they're trying to change the outside of themselves to have the complete outer energy level. We call that the magic number. Maybe I'll go back in our notes and we'll put magic number. We will be defining the next unit as a complete outer energy level. The magic number is just indicating that we have a complete outer energy level, and that's exactly what all atoms want to do. Now, let's take a look at column 7A. When we take a look at column 7A, now let's pick neon to start with. Actually, sorry, neon's not in column 7A. Let's pick fluorine to start with. So if we look at fluorine, we have 2 energy levels. And on the outside, because it's in column 7A, we have 1, 2, 3, 4, 5, 6, 7 electrons on the outside. Let's take a look at chlorine underneath. Now we have 3 energy levels because chlorine is in row number 3. And it also has 7 electrons on the outside. 1, 2, 3, 4, 5, 6, 7. And now let's slide down to something like iodine. Jump all the way down to energy level number 5. 1, 2, 3, 4, 5. So it's in energy level number 5. And it's also in column 7A. So it has 1, 2, 3, 4, 5, 6, and 7. All of these are very close. All of these in the same group, same column, same family are very close to having a full outer energy level. They're only 1 electron away. So in each one of these cases, it's going to want to add 1 electron to their outer energy level to be full. So what happens is we had a neutral atom with a certain number of protons and a certain number of electrons. But this time we added 1 negative electron. Because we added 1 negative electron, it doesn't matter what these numbers were. If it was 15 and 15, 20 and 20, 25 and 25, if you added 1 negative electron, you have 1 more negative electron than you have protons. So all of these become a 1 minus ion. I get students that I ask them, column 7A, what happens to the atom in column 7A? And they get very nervous. And they say, oh, 7A atoms, they turn into a 7 plus. And I say, what? And they go, oh, no, a 7 minus. And I said, what? And so this 7A, we just have to think about it for a second. The 7A indicates we have 7 electrons on the outside of the atom. Every atom in column 7A has 7 electrons on the outside. So it wants to get 8 because of that magic number of being full. So we can understand that it's going to gain 1 electron. When it gains 1 electron, it's going to have 1 more negative electron than it will have protons. So it becomes a 1 minus ion. So everybody in column 7A, the atom is changing to an ion, and it's changing from a neutral atom to a 1 minus ion. So when we look at column 7A, above column 7A, we can write a 1 minus. It's not anything we're going to memorize. We're going to be understanding based off the structure of the atom. Now, let's take a look at column 6A. In column 6A, if we were to pick some elements, column 6A, let's start with oxygen. So if we picked oxygen and we had 2 energy levels, and in the last energy level we had 1, 2, 3, 4, 5, 6, and then in sulfur we have 3 energy levels because it's in row 3, and we have 1, 2, 3, 4, 5, and 6. And then finally, we'll jump down to tellurium in row 5, 1 energy level 5. And we have 6, 2, 3, 4, 5, 6. So now in column 6A, the same group, same column, same family, all have 6 electrons on the outside. Because we're dealing with that magic number of having a complete outer energy level, and we're trying to get to 8 electrons, now I think that you can see this 1 oxygen atom is going to try to gain 2 electrons. This 1 sulfur atom is going to try to gain 2 electrons. And this 1 tellurium atom is going to try to gain 2 electrons. So that it will have 8 on the outside, 8 on the outside, and 8 on the outside. So now, when we're looking at the number of protons and the number of electrons, we don't have the same number of protons and electrons anymore. We have 2 additional electrons. We added 2 negative electrons. So now we end up with a 2 minus ion, because it doesn't matter that oxygen has 8 protons and 8 electrons. When you add 2 negative electrons, the electrons are winning by 2. It doesn't matter that sulfur has 16 positive and 16 negative electrons. When you add 2 negative electrons, you have a 2 minus charge. Same thing with tellurium. So now in column 6A, we take an atom that's not happy. It wants to change its outer energy level into an ion, and we change it from a neutral atom to a 2 minus ion. So when we go to our periodic table, we're adding a 2 minus at the top. That is nothing to memorize. I know that we can figure it out by understanding column 6A has 6 valence electrons. Therefore, it wants to add 2 negative electrons. All of these in the same group, same column, same family will be a 2 minus charge. Now, how about column 8A? When we are dealing with column 8A, let's take a look first at helium, energy level number 1 with 2 electrons. Right below is neon. Neon with 2 energy levels and 8 on the outside. Krypton. Then xenon. Xenon is in column 8A, and it's in row 5 with 8 valence electrons. Now, let's take a look. Our magic number in order to have a complete outer energy level number 1 needs 2 electrons. Every other energy level needs 8. So here, energy level number 1 already has 2. Therefore, this outer energy level is full. Neon already has 8. Outer energy level full. Xenon, outer energy level full. So when we talk about column 8A being full, the atom, all of these atoms, and I'm going to put an arrow, then I'm going to put a big X through the arrow, changing from an atom to an ion. These 8A are called noble gases, and they do not want to change from an atom to an ion. They do not want to change. They don't want to gain electrons, and they don't want to lose electrons. 8A is stable. The atoms are stable. They do not want to lose or gain negative electrons. So we would not even add a number up to here. Maybe we write stable. They don't want to change. Now, let's go back and predict 3A and 5A. My hope is that you would be able to understand that everybody in column 3A has 3 electrons on the outside. So there's 2 options. You could gain 5 electrons to have 8 on the outside, or you could lose 3. It'll be easier for the 3A's to lose 3 than to gain 5. When you're losing 3 negative electrons, you become a 3 positive. Let's take a look at 5A. 5A has 5 electrons on the outside, so it could either lose 5 electrons or gain 3. Because it's easier for it to gain 3 than lose 5, when it gains 3, it would turn into a 3 minus charge. The one that we have left is column 4A. And column 4A is right in the middle. Is it going to gain 4 or lose 4? What we will find out in a future unit is that these in column 4A really like to share electrons. So instead of gaining or losing, they really like to share electrons, and we're going to leave that information for a future unit. I hope this helps in understanding the atom wanting or desiring to have a full outer energy level and changing the outer energy level by either losing electrons to form positive ions or gaining electrons to form negative ions, or staying just as they are because they're already complete in their outer energy level.